Alright, so for this problem, we've got a ladder with negligible mass. It's propped up against the wall as shown here, so it's 5 feet from the corner on the bottom and 20 feet up. And it's got supporting a 120-pound weight, presumably a person. And we want to find the forces of the contact points A and B. And part of the problem, we're also told that surface up at A, this is a smooth surface, which means we're going to have just normal forces. And down at B, it's a rough surface, which means we're going to have normal forces and friction forces. So this is going to be an equilibrium problem. As part of the process for any equilibrium problem, first thing we need to do is draw the free body diagram. So we're going to separate our ladder from the surroundings. So let's go ahead and draw our ladder as so. And we're going to use just the regular X and Y coordinate system. So X is horizontal, Y is vertical. And on our ladder, we've got a few forces that are going to be acting. So we know about this 120-pound weight force. And we're going to have a few other forces. So in addition to the 120-pound weight force, we have a normal force acting at A. And so the normal force is going to be perpendicular to the surface. So it's going to be going out like this. And we're going to call this one FAX. I know I've got a normal force down at the bottom at B. And this normal force is also perpendicular to the surface. It's going to be going up. So I've got FBY, because this is going in the vertical direction. And then finally, I've got the friction force. So the friction force acts parallel to the surface. And in this case, I'm going to guess it's going to be pushing this way. And I'm going to call this one FBX. And there's no moments. With these points of contact, we have no moment existing. And like I said, there's no friction force at the top. So here we have our free body diagram. We've got one known force, this 120 pounds, and three unknown forces, FBX, FBY, and FAX. So we need to start drawing out our equations of equilibrium. So I'm going to make a little more room over here. And I go through one at a time. Sum of forces in the X is the first one. And in the X direction, I've got two forces, just FAX going this way and FBX going this way. So FAX going in the positive direction minus FBX, it's going in the negative direction. And other than that, I just know that the sum of the forces in the X direction has to be equal to 0. So sum of forces in the Y, my next equilibrium equation. I know I've got FBY, it's positive, so I've got FBY, and I've got a negative force, this negative 120 pounds in the Y direction, so minus 120 pounds. And the sum of those two forces, or sum of those forces, has to be equal to 0. Finally, I need to go ahead and take the moment about some point. So, sum of moments, and I've got kind of three different options. I could do it here, in the middle, or down here. I'm going to choose the sum of forces about point B, and that makes it's going to be the easiest because I've got two unknown forces here. So because all the moments are going through that point, or some of the forces are going through this point, I don't have to worry about these two unknowns. So sum of moments about point B, and it's going to be force times distance. So FAX, if I go back to my diagram, I can add in some of these distances. So I'm looking for the distance vertically here. This is going to be 20 feet. That one is pretty simple. And this will cause a negative moment about that point. The one I don't know, that's going to be a little more difficult is I need to know this distance, we call D, here. So that is the perpendicular distance for the 120-pound force, the moment that that force is going to exert. So I can use a little bit of math to solve this. So in my original problem statement, I saw that this 120-pound force is 15 feet up. So I've got 15 feet here. And I've got kind of a triangle. And if I kind of expanded this triangle out, I'd have the whole thing is 20 feet. And I know that this distance here is going to be 5 feet. So what I can use is actually the proportion. Since it's the same triangle, I know that 5 feet over 20 feet, because this distance, this side of the triangle right here is D, it's what I'm looking for. So 5 over 20 is going to be the same ratio as D over 15. If I solve this whole thing out, I end up with D equal to exactly 3.75 feet. So that seems about right. If it's 5 feet from here over to the furthest edge, 3.75 feet seems like a reasonable amount for that distance D. So now I've got distance D. I can bring that back over to my moment equation. So again, FAX, so force times distance, and then it's a negative moment, so negative 20 times FAX plus, as this 120-pound moment, or force is causing a positive moment with the right-hand rule, so plus the distance D, so 3.75 times the magnitude of my force, 120 pounds. And that whole thing, those are the only two forces causing moments, that whole thing is equal to 0. All right, so now I've got my equations. At this point, it's just math. I need to solve for my three unknowns. I've got FAX, FBX, and FBY. So I can do this. Let's start with Fy. So I know that FBY will simply be equal to 120 pounds. All right, that one's easy enough. Next, we can look at the moment equation. I'll notice that there's only one unknown, so FAX. So let's go ahead and solve that. I know that 20 FAX will be equal to 3.75 times 120. Divide both sides by 20. I get FAX is equal to 22.5 pounds. All right, so there's two of my three forces. Last one, I'm going to use the sum of forces in the x. So that one basically reduces down to FAX is equal to FBX. So that's pretty simple. FBX will simply be equal to 22.5 pounds. So there we go. I've got my three unknown forces. I've got FBY, FAX, and FBX. And since all of these are positive, that indicates that the vector arrows I've drawn over there are all pointing in the right direction. So FAX is pushing out from the wall, FBY is pushing up, and FBX, the friction force, is pushing towards the wall. So with that, we solved our problem. Thank you for watching, and I hope to see you again.